I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask that you'd just bless this class. Just help the students understand the material we go over, and just help you, Lord. I just pray that you be glorified in what we do, Lord. In your name I pray. Amen. Okay, so we're working on how to solve systems of differential equations, right? And last time, we found out that we could use these things called eigenvectors, right? So we're still working on systems of ODEs. Principally, at the moment, we're trying to solve dx dt equals to ax, where A is n by n constant matrix. So in other words, this is the constant coefficient problem. And so what we learned last time is that we can calculate, right? So let me just remind you what we did last time. Last time we learned that if you calculate the determinant of A minus lambda I equals to 0 has solutions called eigenvalues. And each real distinct lambda gives x equal to e to the lambda t u a solution, so-called eigensolution. To the problem. Give the problem a name. Let's see here. I would make some overall observations. So basically, to be a little bit more precise, one, there is at least one eigensolution for each eigenvalue. So in other words, if I have eigenvalues 2, 3, and 4, I've got at least 3 solutions, all right? Linearly independent solutions. However, 2, if lambda is a repeated solution to the characteristic equation. What's the characteristic equation? This right here is the so-called characteristic equation. All right. So if lambda is a repeated solution to the characteristic equation, and let's suppose it's repeated with multiplicity, m. So that means that the determinant of A minus lambda I basically is equal to, say, lambda. Well, I need to use a different. Let's say lambda sub naught. So lambda like lambda minus lambda sub naught. I need to use lambda as a variable here, and lambda naught is fixed. So lambda naught to the m times g of lambda, right, with g of lambda not equal to 0. Okay, so in other words, if you factor the characteristic equation, out pops this lambda minus lambda naught to the mth power, all right? If that's the case, then lambda naught is said to have algebraic multiplicity m. So this is, to be more specific, this is the algebraic multiplicity. All right? So anyway, if we have algebraic multiplicity m, then we have at most let's say R equals to m linearly independent eigenvectors. However, R is sometimes less than M is possible. Like last time, we looked at a 2x2 matrix that had a repeated eigenvalue, and we just had one eigenvector. So this R that I'm introducing is the so-called geometric multiplicity. If the geometric multiplicity is like the number of linearly independent eigenvectors for the eigenvalue, all right? When the algebraic multiplicity is matching the geometric multiplicity, that means we've got enough eigenvectors to make the whole solution set. Like if we have that for each eigenvalue, if the algebraic multiplicity is equal to geometric multiplicity all around and they're all real, they're all real eigenvalues, then that means that you've got n linearly independent eigenvectors, and so you can get your n linearly independent solutions, and that's the solution to the differential equation. So if a matrix is like that, all right, if it has the algebraic multiplicity matched by the geometric multiplicity all around, it's a pretty nice matrix. And such a matrix is actually said to be diagonalizable. All right. There's some choice of coordinates where the matrix just takes the form of a diagonal matrix. You can change coordinates to make that happen if it's the case that the algebraic is matching the geometric multiplicity all around for every real eigenvalue. But that doesn't have to be the case, right? Like last time, we looked at what, for example, what was it? Like 2, this one, for example, 2, 2. This has a repeated eigenvalue of 2, and it only has one eigenvector, all right? For example. This has lambda naught equals to 2. It has m equals to, let's say m naught. I should probably call this like m naught. I should probably call this r naught and m naught because it's attached to this particular eigenvalue. If you've got multiple eigenvalues, then you've got multiple algebraic and geometric multiplicities. One algebraic and geometric multiplicity attached to each distinct eigenvalue conceptually. I'm telling you more than you need to know a little bit here because we're really just going to be focused on 2- and 3-dimensional, for the most part, examples, but I'm trying to give you the big picture a little bit here. All right, anyway, so this example has eigenvalue 2 with algebraic multiplicity 2 because the characteristic equation is what? The characteristic equation here is actually just lambda minus 2 quantity squared, right? So you have a repeated root of 2 times, but you just have one eigenvector linearly independent, so the geometric multiplicity here is just 1. So this is an example of a matrix which is not diagonalizable, right? We don't know what to do with this yet. We don't know how to find our second solution. I mean, we found it by explicit substitution last time, but that was kind of a bear. Definitely not the way we want to do it long term. All right, so that's a mystery. What to do when the matrix is not diagonalizable, all right? We'll get back to that. 3, my third observation here, and this is what we're going to be focused on today, is that the determinant of a minus lambda I equals 0 is nth order polynomial, right? In lambda, it could have complex solutions, right? So what do we do with those? We can't ignore them. They're here. Somehow we have to find solutions in that case. All right, so I want to talk to you about how that goes today. Now, sub-comment to number 3. If you have complex solutions to a real polynomial, what can you say about the complex root? What's that? No, like so suppose like f of x is a real, element of the real polynomials. So it has coefficients in R, all right? Then what can you say? If f of 2 plus 3i is equal to 0, then f of what is also equal to 0? I'm stepping away from the lambda for a second here to bring you back to your happy place. Polynomials in x, right? I'm sorry, should I put a t there? Would that make it better? what do we know about real polynomials? They have complex solutions that come in conjugate pairs, right? So if f of 2 plus 3i is equal to 0, then f of 2 minus 3i is also equal to 0. And these are coming from what? These are coming from x minus 2 plus 3i times x minus 2 minus 3i. And when you multiply these things out, these sorts, if a polynomial has these conjugate complex zeros, it means that there was an irreducible factor. There was an irreducible factor. In fact, this one, well, I don't need those parentheses. This irreducible factor in the factorization of f of x is responsible for these complex conjugate zeros, right? When you factor a polynomial, if you find irreducible quadratics, prime quadratics, maybe you call them, ones that when you complete the square on it, you get a sum of squares. Well, those can't be further broken down over the reals, right? Because, this is never 0 for real inputs, but it's 0 when you put the complex inputs 2 plus or minus 3i, right? So that's the kind of algebra we face here. We want to deal with that case. Okay? So let me just, let's work on that. Let's focus on that case then. We still have to, at some point, if I don't yammer on here too long about the complex case today, perhaps we'll get to the mystery of what to do, how to treat this systematically. If I don't get to it today, it's okay, but we might. We'll see. All right, so here's an example. Let's look at an example. Excuse me. xy prime equals to 0, 1. Let's see here. Minus 5, minus 4. xy. Let's try to solve this and see where it takes us. I'll develop the theory alongside this example rather than just, I could go and develop the theory just in the abstract, but I think it's better to work this example in parallel to the theory. So, all right, here's the problem. This problem does not allow us to, well, let's see what happens. What's the characteristic equation here? So this is my A, right? So the determinant of A minus lambda I is equal to the determinant minus lambda 1 minus 5 minus 4 minus lambda. So guys, as you're kind of taking stock of the general procedure for solving these, step 1 in these is to put the equation in the star form like we had at the start of class, right? Step 2 in all of these different cases is to calculate the characteristic equation. For a 2x2 system, that's not a big deal. Admittedly, for 3x3 and 4x4 and so forth, it makes it, this is a computationally challenging problem, right? You definitely want to use technology to sort of protect your logic. Let's see here. There are nice websites to calculate eigenvectors and eigenvalues. I'll share some of those with you maybe a little bit later in this class. So lambda times lambda plus 4. I don't think you need those for 2x2 systems, though. Plus 5, right? So what is this? This is lambda squared plus 4 lambda plus 5, aka lambda plus 2 quantity squared plus 1. So we get lambda equals to minus 2 plus or minus I as the, in this case, complex eigenvalues. Depending on what linear algebra book you read, in fact, most linear algebra books would say that this matrix has no eigenvalues. It has no real eigenvalues, is true, all right? But these are complex eigenvalues, all right? Now, so what do you do is pretty much we just do the same thing we did before, all right? So now that we found our complex eigenvalues, we're going to look for, we want what? I want to throw out this marker. It's worthless. Sad. So we want A times U, right, equal to lambda U. That we want an eigenvector, right? We want to solve that. I would point out that this says that A complex conjugate of u, lambda u. So if I take the complex conjugate of both sides, all right? Let's use star for complex conjugate, okay? In other words, you replace I with minus I and everything. Think about how that works. So this says that A, what's the conjugate of A? Complex conjugate of a real matrix is just the matrix again, right? So when you complex conjugate A, nothing happens. And then you've got the complex conjugate of U, all right? And on here, we've got the complex conjugate of lambda, right? Times the complex conjugate of U. So we find a little theorem along the way here. If lambda has complex eigenvector U, then lambda star has complex eigenvector U conjugate. My point in making this observation, guys, is simply that we can focus our attention on one of the roots, one of the complex eigenvectors, right? And if we find the complex eigenvector for, say, 2 plus I, how do you find the eigenvector for 2 minus I? It's really stupid. You just complex conjugate your answer, and that's the eigenvector for the other root. We don't usually get to do this sort of thing for real eigenvectors, right? If you got one is 3 and the other one is minus 7, you got 2 separate linear algebra problems to solve, right? But so this complex case, well, while involving complex arithmetic at the same time is easier in another regard. So okay, let's get to it. This is not a good way. So what we're going to do instead is look at A minus lambda I times U. That makes the linear algebra go better. And so what that is here is, let's see, my lambda, we're gonna look at the plus one, 2 plus I, all right? So I got minus 2 minus I, 1, minus 5, minus 4, minus 2, minus I. I'll put some dividers in because it's kind of crowded in here, isn't it? And let's say that U has components U and V. All right. If you think about it, U has to be a complex vector. Can you guys tell me why U has to be complex here? It's unavoidable that U be a complex vector. Think about this. A is a real matrix, lambda is a complex value, and somehow the product of these two things works out to 0. If you think about it for a little bit, that means there has to be complex data in U. Otherwise, there's no way you can multiply these out and just get the real 0. So understand, we're looking for a U which is going to be complex. You can prove this in general. If you have a complex eigenvalue, the vector will be a complex vector. It can't just have real numbers or just have pure imaginary numbers. It has to have both real and imaginary numbers as it happens. Okay, anyway, let's look at it then. These, if we did this right, the two equations we get here are redundant, right? On the one hand, we have minus 2 minus I times U plus V equals to 0. On the flip side, the second equation gives us minus 5U. I guess we could do math here, huh? What's that? I'll use plus minus, it's minus 6, right? Did I? Yeah. Minus 6, it's weirding me out for some reason. Minus I, V equals to 0. Just let's check. Let me just briefly check on our calculation here. If you multiply the top, no, I've got an arithmetic mistake somewhere here, guys. let me show you why I think we have an arithmetic mistake. If I multiply this by, let's see here, multiplying by the conjugate of that, which would be minus 2 plus I. Well, minus 2 plus I times minus 2 minus I.
Lambda equals negative 2 plus I? Yeah, that's what I've got.
Ah, I have it up here, and then somehow, thank you. Yes. That's not up for grabs. That minus got to be there. That makes this a plus 2 minus I. There we go. Thank you. I feel much better. See, because now all is well in the world. So yeah, multiply by 2 plus I. There we go. So this should be what? This should be minus 2 minus I, right? Now you can see it. See this, when you multiply these out, you get 4 plus 1, and the imaginary terms, they cancel out. So you get, that's why I multiplied by 2 plus I here, because it's the conjugate of that. So it will give me the length of this complex number squared, which happens to be 5. So this is 5u plus 2 plus iv equal to 0, which of course, if you multiply by minus 1, you get that, right? Okay, I'm comforted. I'm doing a quality check on our calculation, right? You don't have to do this unless you make a mistake like we did. Of course, I did that on purpose. Anyway, so you got choices. You can either use the first equation or the second equation to write u as a function of v, or v as a function of u. I think I'm going to use the first one. I like the first one a lot because that gives me that v is equal to I minus 2 times u, right? Is nice. In fact, I'm going to do what? I'm going to set u equals to 1, hence v is equal to I minus 2, and we get the eigenvector, complex eigenvector, of course, u equal to 1, and then I minus 2. I hope you guys follow what we're doing. It's exactly what we did last time, except instead of having a real eigenvalue, you have a complex eigenvalue. Right? Okay. So what's this tell us? Thus, x of t equal to e to the lambda tu. Now, why was that a solution? That was a solution because if we differentiated it and plug into the differential equation, it works, right? And if you think about the steps we did, chain rule for lambda, and just differentiating and plugging it in, all of those steps still make sense when lambda is complex. So it is in fact still true that this is a solution. However, it's not the kind of solution we're looking for. I mean, to be more precise about what our goal is, what's our goal? Our goal is to find real solutions to star, basically, all right? So this is annoying because we have not found a real solution to star, right? We've just found, in this case, this is what? E to the minus 2 plus I parentheses times time times this vector 1 I minus 2. We found this. This is a complex solution. To the differential equation. So what do we do with this? Right? That's not what we want. Surely it must be some use, though, right? I mean, we must be able to do something useful with this complex solution. Let's see how. I think it pays off here to stop and say something general before we continue with this example, all right? So, me just prove a little theorem for you. If lambda equals to alpha plus I beta is complex eigenvalue of A, all right, and with U equals to A plus IB, the complex eigenvector, where, with respect to lambda, okay? Got to be careful. In general, we got tons of different eigenvalues floating around, so it's important to say which one we're talking about, but that one. Where you could say that A is the real part of U, and B is the imaginary part of U. In other words, A and B are both real vectors. Okay, so if, like, for our example that we were just working, here we have 1 minus 2 plus I times 0, 1. So this is my A vector, and this is my B vector, so to speak. All right? Excuse me. Then, all right, 2 points actually. The first point has little to do with all this. One, if z, all right, equals to x plus iy, where x and y are real, all right, and dz dt equals to az, then dx dt equals to ax, and dy dt equals to ay. Here I'm assuming A is a real matrix, okay? If A is not a real matrix, then that's a different problem. We're not considering that, all right? But for A real matrix, if I have a complex solution like this, right, then the real and imaginary parts of that solution are separately solutions to the problem. Can you guys see why? I mean, it's like the proof of one. I'll write over here. It's really simple. It's just a really short calculation. If I can find the right marker. That's not the right marker. Somewhere here I have a good marker working. So, you know, if we have dz dt equals to az, it says that ddt of x plus iy equals a times x plus iy. But how do we differentiate complex functions? We do it component-wise, right? You differentiate the real part, you differentiate the imaginary part separately, and you add them together. Basically, I is just a constant with respect to the time derivative. So you can pull the time derivative past the I, I mean, pragmatically speaking. So this is dx dt plus I times dy dt equals ax plus iay. This is a complex vector equation, so you just equate the real and imaginary components of it. So the real components are this, and the imaginary components are that and that, so they have to be equal. If you have an n-dimensional complex vector equation, that gives you two n-dimensional real vector equations. One for the real part, one for the imaginary part, and those are exactly what we need to have. X is a solution, and y is a solution. So if this... See, if you should have a strong sense of deja vu, right? I'm just telling you again, when we have a complex solution, we get two distinct real solutions. in there as real and imaginary parts from the linearity of the problem. So this complex solution we found is not useless at all. In fact, it has within it two real solutions, which is all we need for a second order problem, two linearly independent real solutions. Point two, though, so this is like a generic truth. This thing, point number one I wrote here, that's true even for solutions which don't appear from eigenvector method, all right? But point number two, pragmatically speaking, if you've got, let's see here, let's say z, I like to use z for complex solutions. If I got z equals e to the alpha plus I beta t times, a plus ib, right? What's that equal to? If you multiply it out, this is equal to e to the alpha t cosine beta t. Sorry, this is kind of bad math. I'm doing the proof of the theorem and the statement of the theorem. Sorry about that. You guys will forgive me. I hope. Well, I guess you don't have to. So what am I doing there? I'm just writing out Euler's identity, right? How to write the imaginary exponential in terms of cosines and sines. And then you just multiply this thing out. What do you got? There you go. So in particular, we find in the case of a complex eigenvector, complex eigenvalue, you get a complex eigenvector. It has a real part A, imaginary part B, and you put these together, and you get these two real solutions. You get this solution, x1, and this solution, x2. To be more deliberate about it, x1 is the real part of e to the lambda tu, and x2 is the imaginary part of e to the lambda tu. Don't be mystified by these formulas. All we're doing is just multiplying out the complex solution into its real and imaginary parts and saying that those are separately real solutions to the problem. So that's all we have to do, is to take our complex solution and find its real and imaginary parts, and that's the solution set. So like here, going back to our example, I'm going to have to carve myself out I guess I'll do it up here. Example 1 continued. So I don't know, like some people, when they teach differential equations, they just teach these formulas without this discussion. Like here's the method. You have a complex eigenvalue, you find the complex eigenvector, and you use these formulas. That's the solution, right? I want to explain to you guys where those formulas are coming from. But it's a little bit more than that, because I think pragmatically speaking, for me, it's actually easier sometimes to just use this as a guiding principle to construct the solution, right? I don't know. Do you want to use these as a guiding principle, or do you want to, remember these formulas that I've outlined here for a specific example? Which is better, which is worse? I don't know. I don't have a clear sense of it. But here we have z. The one thing I know is you can't say that this is a solution. This is a step on the way to a solution, but it's not a solution yet. E to the minus 2t. And then you got yourself cosine t plus I sine t. And then, let's see here, 1 minus 2 plus I times 0, 1, right? So, let's see here. Let me minimize the writing here. This implies then that, oh, fine. Let me do a little bit more writing. E to the minus 2t cosine t 1 minus 2 minus sine t 0 minus 0, 1 plus I e to the minus 2t sine t, 1 minus 2, plus cosine t, 0, 1. That's the complex solution in explicit gory detail here for this problem. And so therefore, the general solution is c1 e to the minus 2t, this stuff, which I can rewrite as what? That's actually cosine of t, right? Minus 2 cosine t minus sine t, plus c2 e to the minus 2t. This piece here is the imaginary part. So I've got my e to the minus 2t. Then I've got a sine t upstairs. And then downstairs I've got minus 2 sine t plus cosine t. There you go. That's my general real solution to example 1. Most of the reason this example took so long is I had to prove that theorem in the middle of it. But now we know the theorem, so we can use it for future examples. They're actually not that long. What's the fundamental solution matrix here? Do you guys remember the fundamental solution matrix? So fundamental solution matrix, we take x and we just glue together x1 and x2. And in this case, that would give me, excuse me, there's an e to the minus 2t everywhere. I'm just going to leave that out front. E to the minus 2t looks to me like cosine t, sine t, minus 2 cosine t, minus sine t, minus 2 sine t, plus cosine t. There you go. There's the fundamental solution matrix in this case. Yay. I mean, I don't know. There it is. But any questions, you guys? Do you guys know where I got this problem? Can I erase the theorem? It's in your heart now? You assimilated it into your mathematical core? That's good. Oy, oy, oy. Still digesting, yes. Let me show you where I got this problem here. I'll show you the man behind the curtain. What I did was I looked at y prime prime plus 4y prime plus 5y. I thought about this on the way over here because I know that this has lambda squared plus 4 lambda plus 5, lambda plus 2 squared plus 1 as its characteristic equation, which gives me, of course, lambda's minus 2, right? Plus or minus I. And you guys know from your previous work that that's like c1 e to the minus 2t cosine t plus c2 e to the minus 2t sine t, right? And so I know that the system that corresponds to this second order problem has to have sines and cosines in the solution somehow, which to me means that it has to be a matrix that needs a complex eigenvector, right? As you can see, what's the first component? E to the minus 2t cosine t plus c2 e to the minus 2t sine t. See, because the way I found this system was the usual reduction of order. Y equals to x1, y prime equals to x2, right? So x1 prime is equal to x2, and x2 prime is equal to y prime prime, which is equal to, in this case, minus 5x1 minus 4x2 as a system. x1, x2 prime is 0, 1, minus 5, minus 4, and that's how I thought of this problem. I haven't gotten to the point of asking students on tests where I thought of the problem from, though, so you're probably okay. But just to be honest with you, that's where my problem is. I have many problems. This is where this one came from. So. problems I enjoy are mathematical. I brought this book here mostly because it's light. And any good differential equations book is going to have a section on complex eigenvalues. And if it's a really good book, it should have, oh man, the first example, the eigenvalues are 2 plus I. It's slightly different. I wanted something a little bit more different, though. Oh, of course, he's only going to have one example. Oh, no. No, no, no. Here's another one. I'm going to work this next example at normal speed. All right. All right. Here's the problem. Sorry, his notation's weirding me out. But anyway, this should be fine. So example 2. xy prime equal to 1, 10, minus 1, minus 1. xy, let's find the real solution. Find general real solution. All right. So here we go. We're looking at the determinant of 1 minus lambda, 10, minus 1, minus 1, minus lambda, which is lambda minus 1 times lambda plus 1 plus 10, aka, cool, lambda squared plus 9 equal to 0. Therefore, lambda is equal to plus or minus 3i. This problem is going to be nicer than the first one we worked. What is it? Are you wondering about my sign flipping? See, like, I just absorbed, I multiplied minus on both of them. That makes it lambda minus 1 and then lambda plus 1. Just, you know. Okay, so here we go. We'll look at lambda equal to 3i, look for the complex eigenvector. So I'm trying to solve a minus 3ii u, aka 1 minus 3i, put some dividers in here, 10, minus 1 minus 1 minus 3i uv. I'm an optimist, so I'm going to assume we did it right. Assuming we did it right, this second equation is by far the nicest one to work with. Minus u plus, let's say minus u minus 1 plus 3i times v equal to 0. I think solving for u makes sense here. U is equal to minus 1 plus 3i times v. I'd rather have 1 minus than 3 minuses, so let's set v equals to minus 1, then u is equal to 1 plus 3i. Hence, u equal to 1 plus 3i minus 1 is my complex eigenvector. By the way, I could set v equal to like 2 plus 3i or something if I wanted to. These are a nightmare to grade. Unless your students are like autonomous, very robotic and just do what you do. So usually they're pretty easy to grade. But, because usually you guys don't like, you're like, well, Professor Cook usually put a 1 or a minus 1 here, but I'm going to put a 13 plus 17i because I can. No, you guys just don't do that. So like, it's usually not that hard to grade actually. But in principle, you could put any non-zero complex number here and it'd be legit. But anyway, that just corresponds to a relabeling of the, it's more complicated here, but it again amounts to relabeling of the C1 and C2 and like just an intermixing of the solutions, but it's much more complicated to explain. But we have that freedom. See, because you can always take the complex solution, right? I can take this complex solution and I can multiply it by like 13 plus 17i. If I multiply by 13 plus 17i, that's still a solution to the problem. But the real and imaginary parts are totally scrambled, which is like taking some sort of weird linear combination of the original x1 and x2 and replacing it. Multiplying by a complex number like that, it rotates it and dilates it. It's quite awful. But anyway, I choose v equal minus 1. And so with that in mind, this is 1 minus 1 plus I and 3 and 0. So I will use the formula that I erased. This is A, this is B. I can write down the answer. X of t is equal to C1 cosine TA minus sine t. Oh, not, excuse me. What's the eigenvalue here? 3, so cosine 3t. Because that beta is basically, this means beta is equal to 3, alpha is equal to 0 in our previous lingo. So I get C1 cosine 3ta minus sine 3t b plus C2 sine 3ta plus cosine 3t b. Remember the minus here comes from I squared equals minus 1. Anyway, in detail, that's C1. Let's see here. I can do it in my mind's eye. Cosine 3t rather, minus 3 sine 3t from that 3 in the b. And then downstairs minus cosine 3t, 0 here, so no sine t. And then plus C2. Let's see here. I get a sine 3t plus 3 cosine 3t. And downstairs I get a minus sine 3t. There you go. That's the general real solution here.
So, could you theoretically come up with a generic form for your answer? Like x, y prime equals to a two matrix A, B, C, D, and then solve it out with that? I mean, I know it's not the most instructive to simply plug and play after that. But can you do that?
I don't know what you mean.
Like rather than using constants 1, 10, negative 1, negative 1 in our original problem statement, could we use arbitrary variables A, B, C, D?
Oh. Well, if I replace 1, 10, 1, minus 1, and 1, minus 1 by A, B, C, D, then it's rather complicated because that's going to have to cover all 3 different cases, maybe 4 cases. Distinct real case, repeated real case, not enough eigenvectors, repeated real case, enough eigenvectors, and this complex case for arbitrary ABCD. So in practice, I don't think such a formula would be helpful. Possible in this case? I mean, imagine so. Everything we're doing here is pretty algorithmic, so yeah, you could come up with some sort of uber formula to do this, I suppose, yeah. But I've never done that. All right, so there's two good examples for you, which I think is enough. Let me show you some more with the computer. If I can get it working. Now, I've been focusing on the 2 by 2 case, right? But you can easily do 3 by 3 problems by nearly the same. I mean, the algebra of this algebra gets a little bit more muddy. Let's look at that actually for some specific examples here. I'll show you as soon as I find my. All right, media is present. Acknowledge it. Okay, good. You know, when you don't acknowledge people, it can be very bad. If there's anything we learned from Naruto, it's that. Let's see here. You guys don't read the Naruto? Naruto? No? All right. They become unfathomable monsters, of course. To gain attention, basically. But don't worry, eventually they'll be Naruto's friend, so it's okay. That much we can be pretty sure. Where'd I put this silly thing? All right. So it didn't turn off the lights this time. That's weird. Huh, interesting. I really wanted it to turn off the lights. Front off. Front off. Front off. Back off. Okay, well, we tried. That's weird, right? It's weird. I'm not sure what happened there. Anyway, let's see. Let me get past here. Here's the real ones, right? So here's another complex example. This one's just like the ones we just worked. 0, -1, 4, 0. This says lambda equals to plus or minus 2i, and we get this complex eigenvector algebra. It leads me to this eigenvector. Any choice of u will work. I'll probably make u equal to 1 if I had to guess. I make u equal to 1. Yep. And so that gives me the complex solution, cosine t plus I sine 2t times 1, 2i, which multiplied out to give me that. And here I'm explaining the real and complex solutions are both solutions. I mean, the real and imaginary part are both solutions, right? So that means that that and that are separately real solutions from that single complex solution like we've been talking about. And so there's your fundamental solution matrix. That one's a little bit prettier. All right. Here's an uglier one. We already did these today. Let me go on here. I'm trying to find something a little bit more exciting. Here's 3 real eigenvalues. And they're distinct, so there's going to be one eigenvector for each. So we'll get this vector, that eigenvector, that eigenvector. I need my laser. So we get from these 3 eigenvalues, 1, this one is with 2, this one is with -3. We get these 3 eigenvectors, right? And so then we put together the solution. It's a 3 by 3 problem, so we have 3 solutions. And here they are, e to the t, that eigenvector, e to the 2t, that the eigenvector for 2. Here's e to the -3t times, and this is the eigenvector for -3. And there you go. That's the general real solution to this 3 by 3 problem. There's the fundamental solution matrix, which is just formed by gluing these guys together. Here's another one. This one, I think I did these last time, but I'm going to talk about them again because I think it's worth our time. So this problem has a repeated eigenvalue of 2, all right? That means the algebraic multiplicity is 2 because 2 is repeated 2 times. The algebraic multiplicity of 3 is just 1. There's just one factor of 3 in here. And so in this case, you're able to get for eigenvalue 2 This is sort of the generic eigenvector. And so you've got two free parameters here, the u and the v. So you can set one to 1 and the other one to 0, or you can set the one to 0 and the other one to 1, and that will give you two linearly independent eigenvectors. So in this case, the geometric multiplicity of 2 is also 2. This matrix is diagonalizable, right? You can do a similarity transformation to the matrix and make it have diagonal form 2, 2, 3 for what it's worth. Yes, Luke?
Is the algebraic multiplicity of the matrix determined by the fact that it's 2 that's repeated, or that's repeated twice?
That it's repeated twice. And the algebraic multiplicity is determined solely by the algebra of the characteristic equation. Geometric multiplicity is determined also by algebra, but by the algebra of the particulars of the eigenvectors. It's a more subtle thing, what makes geometric multiplicity be 2 versus not 2. That's really one of the central questions of linear algebra. But anyway, so here's the next problem. This one has, again, these examples are pretty good. This has eigenvalue 2, again algebraic multiplicity 2, other eigenvalues 3. However, when you look for eigenvectors with eigenvalue 2, you only find 1. So the algebraic multiplicity of 2 is 2, but the geometric multiplicity of 2 here is just 1. On the other hand, 3 is an eigenvalue, so you always find at least one eigenvector for each distinct eigenvalue. In the case of a complex eigenvalue, you find at least one complex eigenvector and correspondingly 2 real solutions, right? You can also have repeated complex eigenvalues. That's also possible. And you may or may not have as many complex eigenvectors as you have repeated complex roots. The same thing can happen with the complex eigenvalues. You could have an eigenvalue of 3i plus or minus 3i repeated, and you might only find one complex eigenvector. That can happen. So anyway, long story short here, I only find these 2 real solutions. It's like, well, what's missing? Because it's a 3 by 3 problem, right? So there's some other solution we don't yet have here from the eigenvectors. Here's another one, 777. This is, eigenvalue repeated 3 times. And in fact, any vector is an eigenvector with eigenvalue 7 for this matrix. It's really, really easy. You don't really need to do algebra. This is the general solution. In fact, if you just kind of go back to this and rewrite it as a system of scalar equations, it's dx dt equals to 7x. It's dy dt equals to 7y. It's dz dt equals to 7z. So you can integrate every one of those stupid things separately and just write down this solution immediately from just basic first couple week technique stuff. Like separation of variables will kill this. There's really don't need all of the beast, the full machinery of the beast here. All right, what's this one? Here's a different, so basically this series of examples explores all of the different nooks and crannies of the third order system. Like there's a lot of different things that can happen. This one has a repeated eigenvalue of -2 3 times, right? And when you go to look for eigenvectors with eigenvalue -2, you're faced with this matrix. This is a kind of interesting matrix because it's got just one equation, right? This just says for u equal to 0. That says u equal to 0. So I guess we could be sure u is equal to 0. But on the other side of things, v and w, they're free. So this time we get a generic eigenvector looking like this. If you put v equal to 1, you get 0, 1, 0. If you put w equal to 1 and v equal to 0, you get 0, 0, 1. We've got 2 linearly independent eigenvectors here. But we have an algebraic multiplicity of 3. So again, not to beat a dead horse, something is missing, okay? What do we got here? This one has a repeated eigenvalue of -1. And this one actually only has one eigenvector. We have algebraic multiplicity 3, geometric multiplicity 1 in this case. See, this is one. This problem is actually one where I would be most comfortable doing row reduction to be sure about this one. You really need